Hello, AP Chemistry students. I hope you're ready to really get into equation writing. We're going to be spending a couple days going over kind of each main topic within this section, and it's going to tie in a lot of the stuff from the summer assignment. So hopefully you're ready to go with that. So let's just go over some basic information when writing chemical equations that's going to help us out as we do any of our types of reactions. So first off, most elements can exist as monoatomic atoms, which we talked about briefly in the previous lesson. However, there are those 7 that cannot exist as monoatomic in nature. So these are our diatomic elements, and you need to know this. Now, one big thing, this is when they are in as a pure element. Okay, this is not going to be the case when they're in a compound. So just keep that in mind. They can have as many as needed based on the bonding involved. This is just when they are a pure element. So here you have like those 7 that you need to know that we talked about. I gave you a couple of examples in the last video, Hoberfinkel, different phrases, 7 up. Also just be on the lookout, not that I usually see these pop up in for us, but you could also have some exceptions for phosphorus and sulfur if those are in as a pure element. The other part is you need to know the phases of our pure elements. And these are their phases at STP, standard temperature and pressure, which is very similar to like room conditions, because those conditions of temperature and pressure would affect what phases they are. So we want to know what they are as pure elements. So you'll see that most of your diatomics exist as gases. So you have hydrogen, nitrogen, oxygen, fluorine, chlorine, and then all the elements in group 18. These are your noble gases. Now, noble gases usually are inert. They don't tend to react, so we won't see them pop up in our chemical reactions over the next few days. There are, though, 2 liquids that you need to be aware of, mercury and bromine. So here mercury is our metal that is a liquid, and bromine is a non-metal, which is a liquid as well. So you're going to have to be aware of those. So just things to look out for as you're writing these. I always get a question when we're dealing with compounds, well, what's the phase going to be? You're going to hear me say a lot, especially when we deal with like synthesis and decomposition, that ionic compounds are going to tend to be solids at room temperature, and our molecular compounds, those can be solids, liquids, or gases. They tend to be more on like the liquid or gases side, so usually you'll get a little bit more information about those in the question. Okay, so just some basic stuff you're going to see keep popping up as we work on our reactions. So today we're going to focus in on just synthesis and decomposition reactions. So with synthesis reactions, you guys should know this is going to be when you have, 2 or more pieces that are going to come together and synthesize one compound. So that's just a general formula. So let's work on how are we actually going to write these out based on what we know. So write a reaction for the synthesis of gaseous hydrogen iodine. So I'm going to start with the compound that they're giving me. So here I have hydrogen iodine. Hydrogen is going to be +1. Iodine is going to be -1. So I'm going to have HI, and then the phase, make sure you're including phases throughout the year, is going to be a gas. So now I need to synthesize this from the pure elements. So I'm going to have hydrogen, which you're going to have to recognize as one of the diatomics. 2, you also have to know that it's going to be a gas, which again is right up at the top of your worksheet. Iodine, that's also a diatomic, so that needs a 2. And iodine is going to be a solid. So if you look up here, we have the first part of the diatomics that are gases. Bromine is a liquid. However, iodine is actually a solid. So here we've included the elements correctly. We have our compound correct. So now it's just a matter of balancing it. So I have 2 hydrogens on the left, 2 iodine on the left as well. So I need a 2 in front of hydrogen iodine. So that would be a complete synthesis reaction of hydrogen iodine. All right, now we're going to work on an ionic compound, which is writing the synthesis for iron 3 chloride. So again, I'm going to start with my compound. So iron 3, so iron is going to be +3. Chlorine is going to be -1. So with that being said, I would have a formula of FeCl3 in order to make a neutral compound. It's going to be a solid. And then that is my product. So I need to now synthesize that from its elements. So iron exists as monoatomic, so that's just iron. It's one of our solids. Okay, most metals are solids except for mercury. And then chlorine we have to be careful with, that's a non-metal. It's one of our diatomics, so we would have to include the subscript of 2, and then it's also one of the gases at STP. Okay, so I just get my 2 parts. And then at the end, it's really important that we need to make sure we've balanced this, we've conserved mass in this reaction. I'm going to look at chlorine. I have 2 on the left and 3 on the right. I want to get them both to have 6 then. So I'm going to put a 3 in front of chlorine. I'm going to put a 2 in front of the iron 3 chloride, which gives me 6 on each side. But now with irons, because I have my 2 irons on the right-hand side, I'm going to have my 2 irons on the reaction side. Okay, those are what we're really striving towards when we're dealing with these synthesis reactions, is being able to write those correctly. Now, I do want you to just be aware, because this is going to come up throughout the year, some little facts of we can synthesize compounds from other compounds. So just some common examples, and we'll add to this list as we go throughout the year, is these 3 on here. So in this first one, we have a metal oxide, so we're going to have a metal with oxygen. It's going to be adding to water and producing a base, which for you guys, because we haven't done acids and bases yet, this is just a metal hydroxide. Remember, hydroxide is a polyatomic ion that has a -1 charge. So for example, on this one, we're going to use calcium oxide, which is ionic, so we're going to make it a solid here. And I'm going to react that with water, H2O, which is a liquid. Okay, this is going to undergo a synthesis reaction, so we're going to add these together. So if you think about, you have calcium, which is our metal, and then hydroxide is going to be OH. Okay, because calcium is +2 and hydroxide is -1, I need 2 of my hydroxides to be balanced. And then this is an ionic compound, so we're going to say it is a solid. Okay, if I check, everything's balanced out. I have 1 calcium on the reactant product side, 2 oxygens, and 2 hydrogens. So this is an example of a metal oxide reacting with water to produce a metal hydroxide. For this next one, we have a non-metal oxide that's going to be reacting with water. So similar, except here we're going to be dealing with a non-metal. So here I have sulfur dioxide. So we have a non-metal with oxygen. It's going to react with, and this is usually going to be in the gas state, and then we're going to have H2O. All right, so here we're going to make an acid, which is going to be formulas that begin with hydrogen, except for some organic acids where you'll see this COOH, which we won't get to till later on. So with this one, we're going to put the hydrogens together. So I'm going to put my H2s, and then I'm going to combine this oxygen with SO2, and you can think of this as kind of forming almost like a polyatomic ion, which we won't get into with acids right now, which would be our SO3. And then depending, usually it's going to be like a liquid, but I wouldn't expect you guys to know that right now. So just as long as you can get the formulas right and just know that general formula, you will be good. All right, this last little example is when we have a metal oxide combining with a non-metal oxide. This is going to make a salt. So this is just a compound that has a metal, and it's not like a base or a pure hydroxide. So here we're going to use our calcium oxide. I'm going to combine it with the sulfur dioxide. Okay, this is going to combine together. We're going to write our metal, and then we're going to combine the oxygen with our compound, which would make sulfite, and then label that as a solid here because we're producing an ionic compound. Okay, so just some general formulas, just be aware of them. I want you to really be able to do these top 2 really well, and then just kind of have this in the back of your mind, especially these first 2, because those will come up in various questions later on. All right, our last part is going to be our decomposition reaction, and this is going to be breaking this apart. So we have oxygen, or sorry, not oxygen. We have our AB compound, and it's just breaking apart into its elements. So this is basically just the reverse process of synthesis. Okay, so in this first part, we're just going to deal with those binary compounds. So remember, binary just means 2 elements, and it's just going to break down into its original elements. So in this first one, we have aluminum oxide. So we're going to be breaking it down. So this time, we need to start with it. It has to be our reactant side. So aluminum is going to be +3, oxygen is -2. So when I write this formula, I'm going to need 2 aluminum and 3 oxygen. And it's an ionic compound, so we're going to start with it as a solid. So in this case, I'm going to be breaking it up into its elements. So we have aluminum, okay, which is going to be, it's monoatomic. It is a solid. Okay, and then we have oxygen, which is by itself going to be diatomic. So this needs to be a 2. And then this is a gas. Okay, so I have my symbols, I have it all correct, and I have my phases, so then it's just a matter of balancing it. I would personally work with oxygen. I'm going to get them each to 6. which means I put a 2 in front of aluminum oxide and a 3 in front of O2. Okay, and then I just need to balance out my oxygens, which makes that a 4, which, let me just remind you, just make sure all your coefficients, you can't reduce all of them by the same number. That will show you that you have the smallest whole number coefficients there. Okay, all right, and then our next one here, we're gonna decompose hydrogen bromide. So I'm gonna have HBr, because hydrogen is +1, bromine is -1. We're gonna say, check this gas. Okay, and then we're gonna decompose it. All right, so here I'm gonna have my hydrogen. Okay, this is one of those 7 diatomics, so you have to put the subscript 2, and it's also one of our gases. And then you have to be careful here. Bromine is diatomic, but it's one of those 2 liquids, so you have to make sure you actually label it with an L there. Okay, now that we have the formulas right, the phases are in there, we're just going to balance it by placing a 2 in front of hydrogen bromide. Okay, all right, so that's how you want to be able to decompose your binary compounds. All right, and this next little part is just a reverse of what we saw in the front. You'll see in this first one, we're dealing with our metal oxide. So I'm going to start with kind of the example that I had in the front. So you had calcium hydroxide, okay, which in the front I think I had it as a solid. And then this is just going to break into the metal oxide and water. So you'd have to recognize this as, okay, here I don't have a binary compound, I have a ternary compound. It's a metal hydroxide, so we'd have to know that it's going to break into these 2 products. So in this case, I would have my calcium, CaO. Okay, that calcium with its +2 and oxygen with a -2, I just need 1 of each. And then that leaves you with your water. Okay, this next one is super important. I would put a big star or highlight H2CO3. This is a common product in, not common, but you'll see it in double replacement reactions, and you can never leave it as H2CO3. So this is an acid that contains oxygen. It is going to break down into the nonmetal oxide and H2O. So anytime this year you write down as a product or you write down as something else as H2CO3, you're always going to decompose it further because it's very unstable in this form. So this is going to make your nonmetal oxide, which is going to always be CO2, and carbon dioxide is a gas, and then you're going to have water. Okay, and that's what this little box is over here. H2CO3 should never be written as a reactant or product in reactions on the AP exam. It's always going to immediately decompose into CO2 and water. And you'll see that come up in some labs and practice questions throughout the year. And then finally, we're going to do that last one where you have a salt that contains oxygen. And think of a salt right now as just an ionic compound that contains oxygen. So on the front, we had used CaCO3, and actually I might have used a different one with sulfur, but we're going to use calcium carbonate. So that's going to be a solid. If that undergoes decomposition, it's going to make a metal oxide. So it's going to produce that CaO again. And then in this case, we have leftover CO2, so carbon dioxide gas, which is our non-metal oxide. Okay. All right, one last little thing that's on the bottom here is just be aware of some other compounds besides the H2CO3 or carbonic acid. Stuff like ammonium hydroxide, sulfurous acid are unstable, so they'll decompose into water and a gas. Don't worry too much about that right now. Just be more focused in on those binary, and then just kind of have these guys in the back of your mind. All right, guys, great job, and I will see you soon.